All right.
All
We
right.
made
Good
it.
evening.
Good
We
evening,
are
Joe.
here.
How you doing?
I'm here.
You are here.
Yeah, and
I'm here too.
behind us out on the deck is about 300 people visiting here at the Chabot Space and Science Center, and I think they're all watching on the monitor out there.
Well, they're not all watching on the monitor. They really have better things to do, like look through telescopes. But for those who aren't looking through telescopes, you could watch us instead, and we'll show you some live views through the 36-inch research telescope here at the Chabot Space and Science Center. But before we get started, I want to thank Fremont Bank for supporting our program. And I want to thank everyone who has been making donations and joining as a member at the Chabot Space and Science Center. Please visit chabotspace.org and learn about becoming a member of the Science Center. Or if you are watching on Facebook, we have a donation button, and we can really use your donations. We're not going to be fully open to the public until November, although we are having a special event tonight for our membership. We are not going to be at full operating capacity or ability until November. So we appreciate your ongoing support. Um, Anyhow, it's nice to see people here again. I had forgotten what it was like to have a full deck of people, and it's a lot of fun. And we've gotten to meet some of the people who've been regular visitors on this program and have asked good questions over the many, many weeks that we've been doing this. And they showed up tonight to introduce themselves. It's really kind of cool. All right. Well,
You know what? I'm slowing the telescope over to Arcturus just
oh,
now,
all
Richard,
right.
because I don't think we've focused the camera yet.
No, we haven't done that yet. We were just kind of busy in awe of the crowds.
Yeah.
So let's see what we can do here. I'm going to go ahead and share my screen so people can watch what we're doing at least. Give me a second.
So Richard has a camera mounted on our telescope, our 36-inch reflecting telescope. His camera is a Canon digital SLR camera, and what we have to do is get the camera all focused up here because we've been using this telescope here in the last few days for both visual and camera observing, so it's probably not in focus right at the moment. So,
Well, not only that, I'm not seeing Arcturus.
yeah,
So.
hang on a second.
Oops, careful and don't trip here. Yeah. There it is. Excellent. You're drifting to there we go. So no, Arcturus is not a ring, but this is a great view. This is we could do a star test on Nellie's optics right now. There we go. Excellent. Yeah. All right. So we know everything's working. Do I want to start? I want to start though before we look at anything new tonight. I want to show people some results from last week. And let me open up my desktop here. Hold on for a moment. $7.24. And well, last week we spent a lot of time looking at the Ring Nebula, and I had an opportunity to process some of those images. It was kind of a tough night last week because the seeing was pretty terrible. When I say seeing, I mean the amount of distortion caused by the upper atmosphere. And so everything was really jumpy and would get blurry, but I was able to pick out enough good exposures from last weekend's virtual telescope to get this image of the Ring Nebula. And one of the things you could see here very clearly is the central star of the nebula. The Ring Nebula, of course, is what's called a planetary nebula. And these are very, very common objects in our galaxy and other galaxies as well. And they're the remnants of a star, much like our sun, that have used up their fuel and ejected the outer shells of gas, their outer shells of gas, into space, leaving behind what's called a white dwarf star. And the Ring Nebula is one of the best examples of that. It's a particularly bright one. Some people call it the stellar bagel, because it does look a little bit like
Fuzzy
a bagel
donut.
or the fuzzy donut.
Yeah.
Yeah, and but anyway, this came out okay, and I thought it was a nicer view in this process photograph than we were actually getting live last week. The other one I want to show you, and I think I have to go back to my desktop here to get that, so bear with me. We were also spending some time looking at the Imbrium Basin. Are you able to see that, Gerald?
Not yet, no.
Not yet? Okay, I have to reshare, so stand by. Stop sharing. And go ahead and hit share screen. And this was the sharpest image I got last week of the Imbrium Basin.
Oh, shows, well, actually, yeah, the upper part of the Imbrium Basin.
The upper part of the Imbrium Basin. And this is the Plato crater.
Right.
And that's
Alpine Valley right there.
Alpine Valley, right. And that's what I wanted to make sure I could see in the photograph that I chose. Most of the others were really blurry, and even though we had this focus at the same position the entire time, because of the atmosphere, some would be really blurry, like you were looking through the wrong prescription eyeglasses, and others would be dead on sharp like this one. So I picked out this one. I thought it was pretty good. And thought I'd share it with everybody.
Yeah. And you see the smooth area, if you look below Plato and the valley, right down there, right in the shadow is the large smooth area, and that's the actual Imbrium Basin. It's about 700 kilometers in diameter. It's a very old impact basin on the moon. It's about 4 billion years old. And it was originally a crater, but eventually that crater filled with lava because back then the moon had a molten interior, and it filled the basin with lava, made it nice and smooth, and then subsequent impacts made the few craters that you see in the basin.
And related to what you just said, when this filled up with lava, some of that lava escaped, forming this valley right here.
Yeah,
this is actually a lava chute, right?
Right. It's actually a crack that was propagated away from the Imbrium Basin. And when the basin filled with lava, the lava poured into that crack, making the floor of the crack nice and smooth.
Oh, I see. So the actual impact created the crack, and that filled with lava or a lava flow, making it smooth. I get it. That's interesting.
Right. Yeah. Yeah.
Cool. All right. The last thing I wanted to show you, I'm not done yet.
This is the surprise, huh?
This is the surprise. I got to show you this. All right. So not long ago, I showed an image from J.T. Metsävainio, who is a Finnish astrophotographer. And I had the opportunity to meet him a couple of years back, or a few years back, at the astrophotography conference in San Jose. And I found it amazing that someone who lived in Finland was able to get so much telescope time, because you would think that it would be cloudy all the time. And he said it's cloudy a lot. But he manages to do an awful lot of astrophotography and get some phenomenal results. But in honor of the Apollo 11 moonwalk, which had its recent anniversary, right? He put this together, and I will share my screen. Give me a sec here. Where is it? Here it is.
Roll, please.
So this is an image of the moon that's really a mosaic of the entire transcript of the Apollo 11 mission. And you can see in the blown up circle here, which is just this little bit here, which is next to the Sea of Tranquility. The transcript of the astronauts speaking to one another. And I guess what he did was he took an image of the moon and overlaid it with the transcript that had been morphed into this circular shape, and did some pixel math on the mosaic, transferring the grayscale of the moon onto the lettering to make it match as close as possible. And I don't think anybody's done anything this clever with the lunar transcript before.
So if you live in Sweden, where it's cloudy most of the time, and you're looking for something to do, this is how you spend your time, right?
Yeah, or Finland, right? This is how you spend your life. This proves that they have many cloudy nights in Finland. That's right. Anyway, I thought I'd share this because it's a great piece of art.
All right.
All right. There we go.
Should we actually look through the telescope a little bit here?
Yeah,
got all those people out there waiting to see what we're looking at through the telescope. So we're still on Arcturus. I want to make sure our focus is dead on here. Let me do one thing real fast. You're still in live mode, right?
I am in live mode. Yep.
Oh,
we were pretty good.
Yeah, that was just.
Now you messed it up.
All right. Well, I think that's about as good as we're going to get.
All right.
So where should we go first? M13?
I think M13 is a great choice.
All right.
This is kind of a bright night, and
here we go.
I'm going to shut the observatory lights here.
So we're not going to be able to see this in live stream mode. So Richard will have to take a 20-second image.
Yep. Bear with me here, and we will do 20 seconds. And I think that'll do it.
Yeah. Meanwhile, somebody asked, "Where's John?" Well, John's visiting with his brother tonight, so he was not able to make it. So.
And thank you for asking, because I promised John that he would be missed. and he didn't believe me. All right, let's see how this comes out.
Download that image.
There we go. Play the Jeopardy song. There we go. It's not in focus. So we're gonna have to play with the focus a little bit. Can you find a nearby star?
Yeah, let's go to a closer star here, right here. Let's go back to live mode.
Yep. Okay, yeah, you can see it's got a donut shape there. When I get that centered, we can use the numerical.
Yeah, we actually just went too bright with.
Yeah, it's hard to tell with that one.
With Arcturus, it's just so bright. All right, here we go. Let's see what we can do here. Wrong direction.
All right, that looks pretty decent. We're at 8 point. Yeah, that's probably as good as we're going to get.
About 8.0, yeah.
Yeah. So we'll go back to imaging.
Okay. Go back to M13. Try one more time. Wait, hang on a second here. Let me do one thing real fast. And away we go.
Let me know when we're there.
We're there.
Okay.
All right. So while we're getting this next image, let me tell you a little bit about what we're looking at. M13 is what we call a globular star cluster. Globular star clusters, there's about 150 of them around our galaxy. They're like balls of stars out in space, or think of them as mini or micro galaxies, if you will. So M13 has about 500,000 stars in it. The stars in the cluster orbit around the center of the cluster in highly elliptical orbits, and much better focus there.
Yes.
And they are sometimes very close to the center, and then they orbit far out to the extremes of the view here, and then they swing around, they come back in. When they're close to the center, they're moving very rapidly. When they swing out away from the center of the cluster, they slow down. Eventually they get so slow that they start to drop back in again, and they just do this over and over and over again. The cluster itself is orbiting around our galaxy. It takes about 300 million years for it to make one orbit around the galaxy, but it orbits in a region we call the halo. So if you can imagine looking at the Milky Way galaxy from outside, it looks like a flat disk or plate with spiral arms in the disk, and there's a central bulge in the middle. And then around all of that is this very diffuse, faint, spherical region we call the halo. And in the halo are a lot of old stars, including all these globular star clusters. The stars in the cluster are more than 10 billion years old. They are among the first stars to have formed when the galaxy was forming. So they've been around for a long time. The reason they're all old and there are no young stars in the cluster is because it is out in the halo. And out in the halo, there's not a lot of new gas and dust to form new stars. So there's not a whole lot of new star formation going on in these clusters. So the stars we see are all very old stars. Now again, M13 is one of about 150 globular star clusters orbiting the Milky Way galaxy. And we see globular star clusters around other galaxies as well. So that tells us that globular star cluster formation is a common occurrence as part of the process of forming galaxies. Now, interesting thing about the stars, as you can see, it's very dense near the center, and it truly is very dense. The entire globular star cluster, the M13, is about 110, actually a little over 100 light years across. And there's, 500,000 stars in that space. Now, just to put that into perspective, the closest star to our sun in our part of the Milky Way is about 4 light years away. So if you were to space out stars at 4 light years over 100 light year space, you'd only have 25 stars. But here we've got thousands of stars in that 100 light year space. So there's a lot of stars. They're very close together. They occasionally bump into each other. And certainly if you lived on a planet orbiting around one of those stars, you wouldn't have a nighttime because there would be so many stars so close to you, it would just light up your night sky.
Did you say space out? That's what I've been doing over here.
Hit the replay button. I don't remember saying that, but
yeah, I'm pretty sure I heard you say that.
Yeah. So interesting. There's a book, I believe it was written by Isaac Asimov. It's actually a short story called Nightfall, and it's a science fiction story about a fictitious civilization living on a planet orbiting around a star in a globular star cluster. And they don't have a nighttime except for one day I think it's every 100 years or something like that. The alignment of the stars and the planet is just right so that they get a truly dark night sky. And it's a planet-wide celebration when that happens. So that's a book called Nightfall. And, it's an interesting science fiction story.
It is. It's an excellent one. I highly recommend it. I remember reading it when I was a kid.
All right.
Yeah.
So where are we going next?
Well, we already had a request from the other object that I was thinking about tonight, which is to look at the Dumbbell Nebula,
Oh, okay.
which I
Yep.
think is a good target for tonight, and it's
M
nice high, nice and high.
M27, not too far away from where we are, and where we
Yep.
are, we're very well synced right now. So
Yep. Let me abort this image. So we were talking earlier about the Ring Nebula, which is a planetary nebula, and that one appears to us as a ring, of course, because of the orientation of the nebula with respect to Earth. The Dumbbell Nebula is rotated more or less 90 degrees different from the Ring Nebula and appears quite different to our eye. And you'll see what I mean once we get some photos of it. These planetary nebulas tend to have an hourglass shape to them, but if you're looking down the top or bottom of that hourglass, it appears like a ring. If you're looking from the side, it appears more like, as I said, an hourglass. And this particular nebula looks a little bit like a dumbbell, and I'm not talking about somebody that you're calling a dumbbell, but the type of dumbbell that you might find when you're lifting weights, and that's
okay,
why
we're
it's called
there.
the Dumbbell Nebula. Let me start. I'm going to do a 30-second exposure on this, I think, because it'll be worth the extra 10 seconds.
So this thing is not going to be really bright, but it will be colorful.
Yep. Reset that.
And some people say it looks like a dumbbell. Some people say it looks like a butterfly. You be the judge.
Yeah, you be the judge of what it looks like.
We'll have a naming contest.
We're willing to take live suggestions on what it looks like here. All right, let's see what we get now. All right, we can move it off a little bit to the right.
Yeah, we're a little too far to the west here, so.
Yep.
Okay, I probably just spoiled your image there.
That's all right. I stopped it anyway. Have you moved it?
Yep.
Okay, let me start again.
So we have a computer-controlled telescope, and although it works pretty well, when we make big moves, like from one part of the sky to another, the alignment is not always perfect. It gets us pretty close, but not perfect. And then the camera actually has a smaller field of view than what you would see if you were looking with an eyepiece on the telescope. So sometimes we think we're there and we have to kind of reposition the telescope a little bit. That's not unusual. If you're an amateur astronomer, you know you have to deal with that quite often. All right.
Okay, let's see what he can do.
A little bit better.
Adjust the contrast a little bit. See what I can do here. All right, so for those of you on Facebook, I'm looking on Facebook right now, you could kind of make out the hourglass shape pretty well. For some reason, when we do the translation to Facebook, it actually improves the contrast of these images somewhat, and I'm able to make out the hourglass shape. So if you follow my cursor here, you'll see what I'm talking about.
Now, this is a remnant of a dying star, a star that was once possibly similar in size to our sun. And as Richard said, when it got old, it swelled up and it shed its outer layers. And then what was left of the star collapsed into what's called a white dwarf. In fact,
I'm gonna increase the exposure. I aborted that one and gonna go for a full minute. Maybe we'll get a brighter image.
Next time we get a good image here, we'll actually point out the white dwarf. You can just barely see it right at the center of the dumbbell, if you will.
It's actually right there.
Right there. And you're going to notice some colors. You'll see what looks like maybe turquoise blue and some red fringing. And those colors tell us a little bit about the elemental makeup of the cloud of gas and dust that surrounds the white dwarf. The star had reached a point where it was fusing helium into carbon and then carbon into oxygen, but it still had a lot of hydrogen, and that hydrogen was blown out during that 100,000 year phase when it was expelling gas. And hydrogen, when it's hit by ultraviolet radiation, glows in kind of a reddish color. So you can see the reddish fringe, and that's caused by the hydrogen gas that was blown off the star. Now, the star is surrounded mostly by hydrogen gas, but there was some oxygen also blown off. And when oxygen is ionized by that ultraviolet radiation, it glows in a kind of a turquoise blue-green color, which is what you see there. And that color is very pronounced. And that gives you the false sense that oxygen is the dominant gas. But in fact, hydrogen is the dominant gas. The reason the oxygen is so bright is because when you ionize it, you get what's called oxygen 3. And oxygen 3 glows very brightly, even though the quantity may not be very much. It glows so brightly that it overwhelms the much more plentiful hydrogen, which glows in that red color, but not very bright.
So it's a good time to tell the nebulum story. Because I'm always
nebulium.
Nebulium story. Yeah, I always get a kick out of that.
So when astronomers first started seeing this blue-green color, they couldn't figure out what it was. They couldn't identify it, so they gave it a name. They call it nebulium, since it was in a nebula. These things are called planetary nebula. So they called it nebulium. Later on, though, they realized that it was oxygen in an unusual state, what we call oxygen 3. It's doubly ionized oxygen. And the reason that was a surprise is because in the laboratory, doubly ionized oxygen lasts a very short period of time. It doesn't last a long period of time, but obviously the doubly ionized oxygen in the planetary nebula is lasting a very long time. And it wasn't until much later that they realized that when you're in the vacuum of space and these oxygen atoms are widely scattered apart, that's under those conditions, the doubly ionized oxygen can stay doubly ionized oxygen for a long period of time. So that's when they finally realized that what they were actually seeing was not some strange new element called nebulium. It was actually just oxygen in an unusual ionized state.
Well, it's a great example of how science works.
Yep. We're always learning something new. And a lot of times what we learn when we learn something new, we discover that what we thought beforehand was totally wrong.
Right.
And never is that more true than in astronomy.
Yes. I think you're right about that. Yeah, you're right about that. It's so hard to test astronomical theories because everything is either distant in time or distant in space.
Well, actually, if it's in space, it's also distant in time.
Yeah.
So, yeah, one of the interesting things about space is we're always looking backward in time when we're looking out into space. If you go out into your backyard and look up at the sky at the stars, you're not seeing any of those stars the way they look right now. You always see them as they looked sometime in the past. If a star is, say, 50 light years away, you see it the way it looked 50 years ago. This nebula, I believe, is around 1,800 light years away. So we're seeing it the way it looked 1,800 years ago. And that's true of everything. Even when you look at the moon, The light from the moon takes about not quite 1.5 seconds to reach us. So we see the moon the way it looked 1.5 seconds ago, not the way it looks right now. And light from the sun takes about 8 minutes and 20 seconds to reach us. So if you look at the sun, which I don't recommend, you you'll be seeing it the way it looked 8.5 minutes ago, but you won't see it the way it looks right now because by then you'll be blind.
That's right. You won't. That'll be your last view.
Sun.
That realization will be profound, but that'll be the last time you make that observation. Yeah, we were talking about that today, and we couldn't remember the exact phrase, Gert and I. Something about observing with your one remaining good eye, and from looking at the sun. So anyway, I think let me finish this one exposure here, and we can maybe move on to double star. We haven't looked at double stars in a while, and we can take a look at Alberio, which isn't very far from here.
Yeah, it's actually pretty close here. So.
Yeah, so give me 4 more seconds, and then stop what I'm doing, and there we go. Good. All right.
All right, bear with me here for just a second.
Oh, Tim Thompson, who, by the way, I need to give a shameless plug for. He has a show coming up. I think, Tim, you've got one tomorrow afternoon at 5 or 6 o'clock. Put a link up in the chat here for the Mount Wilson Observatory show, Sunday with Tim. He said it was Ira Bowen at Mount Wilson Observatory who figured out what nebulium actually was in 1927. So Mount Wilson
Who
does
was
it
it
again. Ira Bowen.
So how come we don't call it Bowen? Mulium, whatever.
Because it's too hard to say.
Yeah, really. What was I thinking?
Yeah, Tim, go ahead and put a link up to your program tomorrow, or the one that's coming up anyway, and correct me if I'm wrong about it being tomorrow.
But I think live view. I think we can see it in live view.
Let's see what's going on here. If we can, that would be great. Yeah, hold on. Let me get rid of the distractions here.
All right. Maybe zoom in just a little bit.
Yeah, we could probably work on the focus. Maybe not. It's probably just the same. But all right. So this is one of my favorite double stars to look at. Oh, that's a little bit better.
Yeah.
It's one of my favorite double stars to look at. They're very widely spaced, so it's very easy to see even in a pair of binoculars. And also, you're either a UC Berkeley fan or a Stanford fan, and you can choose one of the two stars, depending on the color.
If you're UC Berkeley, you like them both because they're blue and gold.
Yeah, that's true. I kind of think of it as blue and red, so I think of the blue one as Berkeley and the red one as Stanford.
We always tell people this is the Cal star.
I see conflict where others see other things.
Yeah. If anybody out on the deck is from Stanford, they're going to start throwing rocks at us.
That's right. Well, we're close to Berkeley, so they'll be more understanding.
Yeah. So anyway, you see two stars here. One is blue, one is gold. And those colors tell us the temperature of the star. So the blue star is the hotter of the two stars, and the gold star is the cooler. So I want you to think of a candle flame. If you look at a candle flame, the part of the flame just above the wick is blue. That's the hottest part of the flame. As you go up the flame, it's yellow and then orange, and then the coolest part, the highest part of the flame, is red in color. And the same thing is true with stars. Blue stars are hot stars. Stars that are orange or red are the coolest stars. So we can tell the temperature of these two stars just by looking at their colors, and we know the blue one is the hotter of the two stars. Now you might say, hey, wait a minute, if it's hot, why is it not brighter? Well, it's actually much smaller. And the gold star is much larger in size. And because of that, it fools you. It fools you into thinking it's the closer of the two stars. But in reality, the gold star is the farther of the two stars. The blue star is about 300, I think I read somewhere, 387 light years away. The gold star is actually about 7 or 8 light years farther away. And the reason it looks so much brighter is because it's a star that's starting to reach the end of its life. It has swelled up. As it swells up, the outer layers of the star cool, and we know it's cool because we can tell by the color, but it also gets bigger, and a bigger star has more surface area to radiate light, and that makes the star look brighter. So brighter doesn't always mean closer. Sometimes it can mean bigger. And so that star is actually the farther away of the two stars.
So there was some question for a long, long time on whether this particular double star was an asterism, meaning that the stars appeared to our eye as being a double, but in fact were completely independent of one another, or whether they were in fact in orbit around one another.
Right.
And I think that has finally been resolved.
Yeah, not everybody agrees. For a long time, we thought they were orbiting around each other. And you're right, there's been a lot of debate about that. If they orbit around each other, they have a very long orbital period. But some of the data we have now suggests that they are too far apart from each other. Like I said, some paper I was reading not too long ago said that they are probably 7 to 8 light years apart.
That's a long way,
yeah,
for gravitational attraction to create an orbit. It's interesting because I know that when Hipparcos, the Hipparcos satellite, was designed to look for changes in position very precisely of stars all over the sky. I did take a look at Albireo, and that's when there was some change in opinion about whether they were in orbit around one another or not, and towards the positive, that in fact that they were. But then since then, there have been additional studies which call it into question. So we may never know whether they're really in orbit around one another. They're probably influencing each other's orbits as they pass by one another, but they may not make that full loop. But maybe we should look at one where there is no doubt. That's also nearby. So it was suggested by Bob Schock that we point the telescope at 61 Cygni, which is not far from let me Albireo.
Move some stuff out of the way here so I can set it up. 61. Hopefully it'll take it this way. Yep. All right. Here we go. While we're waiting for that, I see another question about the moon wobble.
Oh, yeah. There. Well, I've been seeing worse and worse headlines about this all week long. I saw one which actually said the moon changed its orbit.
Yeah.
And there's a lot of bad information.
I think what I'm going to do is next week I'll put together some graphics to explain what's going on, because there's nothing unusual going on. This so-called wobble, I personally think it's a poor term to be using for it.
Gerald,
Yeah.
before you keep talking, let's get this more centered.
I didn't realize we were.
Yeah, I was saying, why can't I see it? And I realized I was way zoomed way in. There we go. All right. So, yeah, we'll get back to that question in a second. But what you're looking at is 61 Cygni, which is a binary star system in Cygnus, just like Albireo is a kind of a binary star system in Cygnus. And these are what are called K-type dwarf stars. The K-type indicates the spectrum of the star, which then informs us as to its temperature. And the orbit is about 660 years for these two to go around one another. So they're pretty far apart. That's getting into Albireo territory, right?
Yeah.
But that there are real orbital elements that have been calculated for this pair. We're looking at one of them at magnitude 5 and the other at magnitude 6. And this pair was first noted in 1804 when Giuseppe Piazzi, an astronomer, an Italian astronomer, noticed its large proper motion. He was able to detect motion over time through subsequent observations. And so astronomers have studied this pair of stars for a couple hundred years. And it's become a notable double to look for.
Piazzi also is famous for having discovered the dwarf planet Ceres.
Oh, that's right, and which was a big topic tonight.
Yeah.
We had a speaker earlier who spent a lot of time talking about Ceres. So this is a lot closer to Earth than Albireo. We're looking at 10 or 11 light years away. So this is in our immediate neighborhood. And that's one of the reasons that the proper motion was detectable.
Yeah, proper motion, by the way, refers to the motion across what we call the plane of sky. So if you imagine these two stars were on a surface, like a tabletop or something, moving up and down or left and right, that's what we call proper motion. But since they are actually in three-dimensional space, there is another motion which is toward us or away from us. That's called radial motion. And radial motion is a little bit harder to measure. You can't see it. You have to use things like Doppler shifts and so on to see that. All right.
Yeah, there we go. So let's get back to that question about the moon, because I think
I was hoping we could forget about it.
No, I don't think we should. I don't think we should. I think we have to. It's our job to combat the bad headlines.
Okay.
About this thing. So.
All right. So here's the deal. The moon orbits. Its orbit is tilted relative to the ecliptic. So the ecliptic is the plane of the Earth's orbit around the sun. If you imagine the Earth orbiting in a circle or almost a circle around the sun, it forms what we call a plane, like a flat surface, imaginary flat surface. We call that the ecliptic. The moon's orbit is tilted to the ecliptic by about 5 degrees, and it is tilted relative to the equator of the Earth. Because of that, over long periods of time, the maximum shift in the altitude of the moon above the horizon changes. And sometimes as it crosses the meridian is an imaginary line from the south pole of the Earth through the zenith to the North Pole. If you, why don't we get out of your screen share here for a second so people can actually see. I'm waving my hands here and nobody's seeing it. So,
okay.
so
you need to see you gesticulating.
Yeah.
All right.
So if you imagine an imaginary line from the south pole of the Earth through the zenith straight overhead to the North Pole of the Earth, that is what we call the meridian. And when the moon crosses the meridian at nighttime, you see it. Sometimes it's very low in the sky. Sometimes it's very high in the sky. It can be quite high, almost straight overhead for those of us living here in the Bay Area. And how high it goes or how low it goes varies over time. That's the wobble that we're talking about, is how much it can vary high or low. And it varies over time. It takes about 18.6 years to do the full cycle from going maximum to minimum and back again. So that's the wobble that we're talking about. And because it can be higher or lower relative to, say, the Northern Hemisphere, it affects the tides differently. And so what we're approaching is a period when the effect on the tides will be greater than on average. And so there was a recent publication that said, gee, if you throw in that effect on top of the rising sea level because of global climate change, it actually will amplify that effect. And so we'll get even more shoreline flooding and so on and so forth. That's all they're talking about. There's nothing unusual about this wobble. It's not something that we just discovered. It hasn't changed where the position of the moon or the distance of the moon or how long the moon takes to orbit, any of that stuff. This is a normal phenomenon that goes on every 18.6 years, except that the 18.6 years ago, sea level wasn't as high as it's going to be 18.6 years from now. So that's all there is to it.
Yeah,
Okay.
it's a great explanation,
Yeah.
and it's less dramatic than saying the moon has been thrown out of its orbit, or whatever types of headlines we've been getting.
Don't worry, we'll send Bruce Willis up there to knock it back into its orbit.
We'll send some rockets up. That's right. I'd like to answer Stephen's question. Stephen asked a really good question. Can Nellie observe gravitationally lensed objects? Well, I'll tell you, it's a tricky question. Technically, we have enough aperture to see gravitationally lensed objects, but we are challenged by our actual physical location, which is in a major urban area. So most gravitational lensing is taking place in galaxy clusters that are fairly dim and kind of hard to see, even in a nice dark sky location. But, and I'm going to share my screen here, I believe there is one gravitationally lensed object that we can see. We might have to use it, view it photographically, and that is Einstein's cross. And Einstein's cross looks something like this. And what it is a quasar, and a quasar is an extraordinarily bright, distant object whose natural history is still under some debate. And there's a lot of belief that it is the final part of a galaxy's life cycle, where the central black hole is ejecting, or the space surrounding that central black hole is ejecting large amounts of hot gas, causing an extremely bright eruption. And these quasars are fairly well known. There's a lot of them that are known, and they're all extremely distant. They're coming from from very old galaxies. And this particular quasar has a foreground galaxy in the way that is causing what's called gravitational lensing. So the light is aimed at that galaxy that's midway between us and the quasar, and as it approaches that galaxy, the light bends around it, and so the one quasar becomes 5 points of light. The center point of light being the actual quasar, and the 4 points of light around it being the exact same thing, but lensed by intermediate high gravity galaxies. And this is an object I've seen naked eye in dark skies in California with large aperture telescopes, maybe 20, 24 inches. Nellie, which is a 36-inch telescope, should be able to see this photographically, I would think. I don't know if we've ever tried.
Well, I don't know about this one, but we have imaged a gravitationally lensed quasar. And if I can share my screen.
Please.
All right.
Do you have rights, or do I need to turn that on? Let me make sure.
It's disabled.
Okay, hold on for a moment.
Enable.
I'll go ahead and enable you. Hold on for a moment. Let me stop sharing here and turn on all participants to share. Okay, go ahead.
All right. Okay, so look right here.
Oh, there you go.
This is a quasar that is 9 billion with a B light years away.
I told you these things were far away.
Like 3/4 of the way to the beginning of the universe. And we see a double image, and that double image is caused by gravitational lensing. So that quasar is way, way out there. A quasar is a young galaxy with a very active black hole at the center. It's producing a tremendous amount of energy, often comes off the poles as like beams of energy. And if they happen to be pointed in our direction, we see them very bright. And between us and the quasar is another more normal galaxy, and it is gravitationally lensing the light. So instead of seeing one image, we're seeing two images of that distant quasar. And this was shot with our 36-inch telescope here.
This is awesome. I've never seen this shot. Who took it?
Conrad did.
Conrad did it.
Yep.
It's great.
Yep.
That's a really great example. Erica wants to know why the one I was showing is called Einstein's cross. Well, the whole notion of gravitational lensing and the ability of a massive object in space being able to cause light to bend much the way in much the way that a lens bends light, that was hypothesized by Einstein, and as observations were made of this object and others, it was appropriate to name one of them after him. So Einstein's cross is is a quasar that's been lensed, much like the one that Gerald just showed you, but it was named after Albert Einstein.
Okay, I see a comment there about an asteroid impact in 2030, and I'm sorry, that ain't going to happen. so wherever you're reading that, don't read that anymore.
Don't read that anymore, right? Was that on YouTube or on
YouTube,
Facebook?
Yeah,
okay, good. You're keeping an eye on that.
Yeah. Yeah, once in a while, we get these things come up every once in a while about, oh, we're going to get hit by an asteroid in so many years, and it's almost always fake news. If you hear it from NASA, then it might be real, but most likely if you hear it from, some fly-by-night website, it's fake news. So we are not going to be hit by an asteroid. His note says it's 62 miles or so in size. I guess that's the size of it. Yeah, it ain't gonna happen. Sorry.
Well, good. I'm glad about that.
Yeah.
We got enough to worry about.
Yeah, there are no near-Earth asteroids that are 62 miles in size. The largest one is 26 miles in size, and it's not going to hit us anytime in the next 200 years or more. So put your hard hat away.
Yes, that's right.
All right, well, where are we going to go from here?
Well, I got to ask you some questions perhaps about what is within the range of the scope and see if anything else on my list is a possibility. I don't think we're late enough in the summer yet to be able to catch Sagittarius objects, are we? Are we yet able to do that?
Yeah, maybe.
I'm just wondering if
Yeah,
we're able to
it's
get
not
M.
on it's not on Meridian yet. So
Are we able to get M17?
well, let's see. Let me plug it in and see what it says. Oops, didn't want to do that. Maybe.
It's a maybe, I know.
Yeah. Let's see what happens
Well, let's
here.
give it a shot.
It's
And
going to be
we'll keep working on it, and
I'll
then
tell
every
you,
week it'll be better.
I'm going to go down to Altair first.
Good idea. Yeah.
Or something first to kind of give us a star to sync on.
Oh, not bad.
You need to share your screen here so I can see it.
Oops. Yeah, I guess my commentary isn't enough here. Let me get the. Sorry. Actually having trouble doing that. Here it is.
Don't see it yet.
Yeah, no, I found the right control. That was my excitement. Here we go.
Okay, so let's see. Got to go down a little bit.
Let me get my target.
All right.
Perfecto.
We're there. So now let's try M17 once more. And looks like we can do it. Yeah, it's actually fairly close to the meridian.
Oh, that's not bad. Okay. All right, we'll give it 30 seconds. So M17 is known as the Swan Nebula, and it is not a planetary nebula like we've been showing you during these spring and early summer months, but is a reflection nebula. So it's a star-forming region that has a lot of gas surrounding it, and that gas is illuminated by the stars that are being formed in the vicinity or that are already in existence in the vicinity, reflecting that light back to us. And let's see if we can get anything. Yeah, there we go.
That's see. Not bad. Not bad.
It really is not bad at all. Let's see if I can bring out some contrast. There we go. And I want to see what it looks like on Facebook when it catches up with us. There. Okay. So the Swan Nebula is actually a pretty big object. We're not seeing the whole thing in Nellie's view here, but
so this is where new stars are forming, right?
Yeah.
Or is it a supernova remnant?
No, it's not a supernova remnant. It is a star-forming region.
All right. So this is a cloud of gas and dust that is condensing to
Bear with me here while I sit there and tweak it. Yeah, that's not too bad. And I'll tell you, it doesn't look much like a swan in this image. But if you were to look at it with a lower power telescope, it would look a lot more like a swan. So yeah, you'll have to pardon our. If we were to flip this upside down, this is like the belly of the swan here, and this is the neck of the swan here, and the head of the swan here. So you have to kind of turn the whole thing upside down to get the swan shape.
Well, I just shifted it a little bit, so let's see what it looks like.
Okay, yeah,
there you go.
And it's also called the Omega Nebula as an alternative. If you don't want to go looking for swans, you could look for Greek letters. All right, that's not bad.
Yeah.
It's a good thing to end our evening with, actually.
Well, there's one other object that I thought we would end the evening with.
Okay.
I don't know that we're going to be able to see it. The dome might be in the way, but let's give it a shot. All right. So why don't you go back to live view when you're ready?
All right. I will do that right now. Let me abort this and go over to live view.
We have a large dome that's to the southeast of the observatory we are in right now, and sometimes it blocks our view of objects, but I think this one is going to be in the right position. So stand by. We ready?
Yeah.
All right, here we go. Now I'm going to go over to the telescope, make sure we're on it.
Yeah, it looks like there's a dome in the way. Oh well. We could look at the lights inside the other dome. That would be a true peeping Tom with a 36-inch telescope. Oh well. Next week.
Well, we'll do this surprise next week.
I know what the surprise is, but I'm not going to say.
Yeah, this is something everybody's going to really like when they finally see it.
Yeah.
And it's just, if we hung around here for about another, looks like about another half an hour, not even that, it would show up. So.
All right. Well, if there's any other questions, now's the time to ask them. We're happy to answer any additional questions, and if not, we'll bid you farewell for another week.
Yeah. I don't know if all the people out there on the deck are still out there.
Yeah, I don't know. I don't hear much noise out there. I see a few people, but I think mostly folks have wandered off.
Yeah, the event actually ended at 10 o'clock. So, yeah. Oh, well.
Yeah. Tim said, I guess we can't point Nellie down at Oakland. Bob guessed what the object was. And Erica said it was an awesome night. And thanks for coming, Erica.
Yeah, it was, Erica has a little girl named Stephanie. She's 6 years old. And they are frequent attendees on our virtual telescope program. And I always enjoy it because little Stephanie asks some really good questions for a 6-year-old. And, I was looking for it. It's been almost a year now that we've been seeing their names pop up on the virtual telescope program. And I was really looking forward to the time when we would eventually get to actually meet them. And tonight, we finally got to see them face to face, and I got a hug from Stephanie, so I was pretty happy about that. And hopefully we're inspiring Stephanie to think about becoming an astronaut or an astronomer or something when she gets a little bit older.
All right. Well, thank you, Gerald, and thank you all for participating tonight, and we'll see you all next week.
Let's see. Somebody asked just now if we can view Jupiter or Neptune right now. Well, definitely cannot see Jupiter because it's even lower behind the dome. And Neptune, we could probably see it, but it's so faint, it would just look like a little blue dot in the telescope. So maybe that's something we ought to think about doing next time.
Okay. Yeah. Well, maybe next time we'll be able to start seeing some planets again, and we'll definitely keep that in mind. So tune in next week for that, and we'll see you all then.
All right.
All right. Take care now.
Good night, everybody.